Section 19.7, fascinating stuff, even more riveting than the first 6 sections of the chapter, right? Okay, here we are, section 19.7, which deals with the hydrolysis of an acetal. I told you the other day we actually used an acetal as a protecting group. Remember that when we took a ketone? Like if I just give you a quick example here. Oh, my Apple Pencil is not connected. There we go. If we do something like this, let's say we took a ketone like acetone, and then we treated it with ethylene glycol, catalytic amount of acid, and we remove water like this, and that you can make an acetal this way, a cyclic acetal. And what I told you is that once you make that acetal, it's actually very stable to base. If you put that in a basic solution, you know, sodium hydroxide or something, it is very stable to that. So we don't have to worry about acetals being labile in base. However, in acid, they're very labile. It says here that acetals are hydrolyzed with aqueous acid to give the ketone or the aldehyde back and 2 equivalents of the alcohol that you started with. The good news is this, is if you understood how acetal formation worked, it's just the reverse of that. Nothing more than the reverse of acetal formation. So you take an acetal, you put it in water with acid, and you end up reforming your ketone, in this case, plus 2 equivalents of your alcohol. If you formed an aldehyde, or if you made your acetal from an aldehyde, then you would form an aldehyde. Again, if you take your acetal and you treat it with base, you get no reaction, right? They're very strong in base, but they're very weak in acid. And notice the difference between these conditions. Here in the hydrolysis, you're actually adding water, whereas here you're actually removing water. I know there's a lot of similarities between the two, but again, it's based on Le Chatelier's principle, right? If you have a whole bunch of water in here, that's going to push the reaction mixture this way, whereas over here, since you're removing the water, it's going to push it in the direction of the acetal. Anyhow, there we go. So let's move on from there and let's take a look at the mechanism in detail. So everybody should be able to draw this mechanism, but before you get intimidated and say, oh darn, this thing is really long, it is the exact reverse of the mechanism of the formation of an acetal. We start by protonating one of the alkoxy groups. Why do we do that? Because this is not a good leaving group by itself. It has to be protonated in order to be converted into a good leaving group. So we protonate that, and then the leaving group leaves. Then it undergoes nucleophilic attack, but now the nucleophilic attack is by a water molecule, right? We're adding water. We're not removing water when we're hydrolyzing the acetal. After 2 more proton transfers, we end up protonating the second alkoxy group, and then we end up losing it as an alcohol. You notice that we lost the alcohol. Where am I here? We lost the alcohol here. We lost alcohol here, and then we lost alcohol here, and then we do another proton transfer to regenerate our ketone. But again, if you look at the mechanism of the formation of an acetal, it's just going backwards like that. And that's based off of something called the principle of microscopic reversibility. And the good news is this, even though the mechanisms aren't shown in our textbook, the hydrolysis of an imine or an enamine undergoes a very similar mechanism in acidic conditions. Now, I'm not going to ask you the hydrolysis of an imine or amine. I'm not going to ask you to write out that mechanism. But again, it's the reverse of the formation of the imine or the enamine. The difference is what? Instead of removing water, we're adding water in acid. And if we're adding water, it's going to push the equilibrium to this side to regenerate your ketone and your primary amine if you have an imine, like we do here, and it's going to regenerate your ketone or aldehyde and your secondary amine if you are starting with an enamine. All right, there we go. And I think one of the most challenging things about the hydrolysis of acetals is not necessarily the mechanism for students, it's usually drawing the products and recognizing the products. So let's take a look and see if we can draw the products of the hydrolysis. We've got 2 acetals, we've got an imine and an enamine here. So we have the whole smattering, if you will, of all the different kinds of functional groups that we've looked at in the last couple of sections. So let's see here. We've got an acetal. Let's investigate this acetal very closely. We have the carbon that has two oxygens attached to it. So we have this carbon here with our oxygen here and oxygen here. So remember, an acetal is when you have a carbon with two OR groups attached to it, right? And then we've got two R groups. This is an acetal. So what happens when you hydrolyze that acetal, you take it and you treat it with water and acid, and that ends up removing both of these alcohols, and you regenerate the ketone or aldehyde, in this case it would be a ketone, on this carbon. So you end up with R, here's my blue pen, you end up with your R group, the carbon, and it gets converted back to a carbonyl, and then you end up with two equivalents of the alcohol like this. So we're going to do the same thing here. We're going to end up breaking this bond and this bond, which is this bond and this bond here. Therefore, what's our carbonyl compound going to look like? Let's pencil it in. We're going to have a 5-membered ring like this. Let me draw it a little better than that. So we have a 5-membered ring like this. And on the blue carbon, I'll put it back here in blue, we're going to have our double bond to oxygen like this. So this is our ketone. And now our alcohols, they just happen to be tethered together in this specific example. So let's write our alcohols. We've got OH, then we've got CH2, CH2, CH2. So let's put those in, CH2, CH2, CH2. And then we have the other alcohol on the same compound. So we have 1,3 pentane diol. Give me a thumbs up if you follow me on that one. The hydrolysis of that acetal. Cha? Okay, well then I'm going to skip B for now, and let's go straight to C, and then we're going to come back to B immediately. So let's take a look at C. You notice that this carbon here is the one that's attached to both oxygens, right? So that is the carbon that supplies the carbonyl. And the rest is where the alcohols come from, right? So our alcohols, again, are going to be tethered together in a chain. So we have them tethered, right, like this together. So what's our carbonyl going to look like in this case? Let's see, we have our carbon, and it's going to have a double bond to oxygen, but what does it got attached to it? It's just got two hydrogens. Like that, it doesn't have any big carbon R groups. So we're going to put our two hydrogens here, and that's formaldehyde. It's the simplest possible aldehyde you can have. And now let's pencil in our alcohols. So we have 1, 2, 3 carbons in the chain that attaches them. So 1, 2, 3, like this. We have our other hydroxyl, and then we have all of these 4 methyl groups on here like that. So another hydrolysis of an acetal. So 2 acetals blown apart. What do we end up with in both cases? We ended up with a diol in these cases. In the first one, we had a ketone. In the second one, we have formaldehyde. Well, let's take a look at B. Could anybody tell me in B, is this an imine or an enamine in B? If I look at this compound here, it's not a trick question. I would never try to fool my students. Would this be an imine or an enamine if I have a double bond between a carbon and a nitrogen? So this would be an imine, right? If we have a double bond between carbon and nitrogen. So if we go back here and we say, okay, we've got a double bond between the carbon and nitrogen. Now the double bond is going to be to an oxygen, and we're going to liberate our primary amine. So let's go back here. And what we're going to do is we're going to cut the bond that I have highlighted in yellow. So we're going to end up breaking this bond here, and that's where our carbonyl group is going to be. So let's see here. We've got 1, 2, 3, 4, 5 carbons, and here is our carbonyl. And our primary amine is going to have a nitrogen with a methyl group, and it's going to have 2 hydrogens attached to it like this. All right, so there's our imine. And in the last one, so let's write this down. This is an imine. And in this one, we have an enamine. And if we go back in our notes, we see that when we take an enamine and hydrolyze it, we end up breaking the bond between the carbon that's sp2 hybridized and the nitrogen, and we form a carbonyl off of that. So let's do that. This is the sp2 hybridized carbon, so that's where we're going to break our bond. And what we're going to end up with is this, where we have our ring that looks something like this, or bicyclic species like that. Now we're going to have a double bond to oxygen from that sp2 hybridized carbon. So we're going to have our double bond off of there, like this, and then we're going to have our secondary amine, which is a nitrogen with 2 methyl groups, so CH3, and we've got 2 of them, and 1 hydrogen, and there you have it. So we've covered acetal hydrolysis, imine hydrolysis, and enamine hydrolysis. Make sure you're able to draw the products of an imine or an enamine or an acetal hydrolysis. Any questions about that one before we move on? And again, I covered the acetal hydrolysis here, and if you go back a couple of slides, or sorry, just one slide, I have the hydrolysis of the imine and enamine. All right, well, let's move on from there, and let's talk about sulfur nucleophiles. I always cringe when I see this at first, because the first interview that I did at a graduate school, the first question anybody asked me in an interview was about a thioacetal, and I actually couldn't answer the question. I said, oh boy, the guy asked me a question. He said, oh, you made this thioacetal, and then he asked me something about it. And I said, oh, jeepers, I'm not actually sure about that. And he turned to me and he said, I don't know either. I just thought I'd ask you. So anyhow, ketones and aldehydes will react with the thiol the same way that they react with an alcohol. And we can end up making a thioacetal. So we're just replacing the oxygens with sulfur atoms here and here. So we get a thioacetal. Again, treatment with 2 equivalents of your thiol, catalytic amount of acid, and of course we remove water from the reaction mixture. And you can also use a dithiol, so this would be a dithiol, and in that case you make a cyclic thioacetal. Either one works, and you might be wondering, well, what can you do with the thioacetal? I'm glad you asked, because thioacetals can be converted to alkanes. Just like we saw the Clemmensen reduction of a carbonyl or the Wolff-Kishner reduction of a carbonyl, now we have another way to reduce a carbonyl, because when you take a thioacetal and you treat it with what's called rainy nickel. So rainy nickel, and rainy nickel is one of those few reagents that it's common, something I've never used, at least not that I remember. It's a nickel aluminum alloy that's kind of porous, and that's how hydrogen gets absorbed on the surface of it. And the mechanism of this is not in our textbook at all. The only thing he says about it is the mechanism is way beyond the scope of our course. So don't worry about the mechanism of rainy nickel reduction, but it's a really robust reaction, works very well, and provides us with another way of reducing a ketone down to an alkane. We treat it with a catalytic amount of acid. Our thiol here, we're using a dithiol, and then you make the thioacetal as your intermediate. So the intermediate here, and I know you all know what it is, but I'll just pencil it in for the heck of it. The intermediate would be this thioacetal, and then that gets treated with rainy nickel, and it gets reduced right down to the alkane. So now you've got, let's list them all. Do I have them on a slide here? No, I don't. We have the Wolff-Kishner, we've got the Clemmensen reduction, and now you've got rainy nickel. And so it says, predict the major product for each of the following. The first one, we're taking a ketone, and we're treating it with a catalytic amount of acid, and this would be what? 1,2-ethane dithiol, and we end up making a thioacetal. So let's draw the intermediate that you would get after the first step. I know it's not asking for that, and I'm sure you can all answer the question pretty quickly. But let's just draw this for fun. So let's draw our thioacetal, which looks like that. And then in the second step, you treat that with rainy nickel, and you end up reducing that right down to the alkane. So you end up with this bicyclic compound here. Give me a thumbs up. Does everybody follow me on that one? just the idea. If you're not connecting the dots, don't hesitate to stop me and ask me about it. Okay, cool. All right, so the next one we have an aldehyde. It's going to be a little different. The same, but different, right? So we're going to form another thioacetal. This time it's going to look like this. So we're going to have a hydrogen atom here. And we're going to have something that looks like this. And then we're going to reduce that down to an alkane. So you could even draw it like this if you want. So you could put your blue hydrogen and then just say, well, I'm adding 2 more hydrogens like this. And that's one way of writing the compound. I would grade that correct. But that's the same thing as just writing 2-methylbutane. So 2-methylbutane would be the answer. You know, something else about rainy nickel, and I'm not an expert in rainy nickel. Like I said, I didn't use it a lot, if I ever used it at all. But I worked with somebody who knew quite a bit about rainy nickel, and it is what we call pyrophoric. Pyrophoric. Does anybody know what pyrophoric means? I'm sure somebody who's a pyromaniac might know.
Is that where it's really explosive?
Yeah, it just ignites spontaneously in air. Yeah. So maybe that's why nobody ever let me use the rainy nickel. They're like, oh, he's going to start a fire or something. No, but you just have to be careful with it. You have to handle it under inert conditions because it just catches on fire. You know, something else that we'll look at later on, and this has got nothing to do with what we're talking about right now. But later on, we'll look at tert-butyl-lithium. So you take the tert-butyl group, and then you have a lithium attached to it like this. So essentially, you have this carbanion, and then you have a lithium cation like this. And that is really pyrophoric too, extremely pyrophoric, very dangerous. And there were some students at UCCS that wanted to use it for a reaction, I don't know, a couple of years ago or something, and they asked me, you know, can you come in and supervise the use of the tert-butyl-lithium? Anyhow, let's move on to section 19.9. I know we've been in class for a little bit, but this is review, okay? Section 19.9, at least the beginning here, is a review because everybody who's hearing the sound of my voice knows about lithium aluminum hydride reduction and sodium borohydride reduction. Why? Because we covered these in the alcohols chapter. Right? Go back to the alcohols chapter, and you'll find all kinds of information in there about lithium aluminum hydride reduction, which was a 2-step process. The first step, you treat the molecule with LAH, and the second step, you treat it with water, and you could put aqueous acid in here as long as it's a mild acid, that would work. And then sodium borohydride is a weaker reducing agent, so it's just one step. You just put in the sodium borohydride in methanol or ethanol or water, and there's probably other solvents that will work too. And it says here that these reductions are carried out under basic conditions because hydrides are strong nucleophiles. All right, let's see here. Basic conditions. So the first step is nucleophilic attack, right? If we're in basic conditions, we don't need to protonate the carbonyl first. Here's our hydride. They chose to use aluminum hydride. Comes in, we add the hydride, we make a tetrahedral intermediate, and then it undergoes a proton transfer in the second step. So this would be step 1, this would be step 2, and you put water in there, and you protonate it. Now, the book even, kind of mentions, he says, well, the mechanism is more complex, considerably more complex than what we have on here, because we're not even talking about the lithium, which can act as a Lewis acid. But he says, don't worry about that. This mechanism will suffice, and you should know this mechanism if you're in this class, and I'm sure you do after studying it in chapter 12. But something that's interesting about LAH and sodium borohydride reduction is that if you have an unsymmetrical ketone, you're going to end up with a racemic mixture, right? Because if this carbon that undergoes the nucleophilic attack by the hydride is sp2 hybridized, that means it's trigonal planar. So the hydride from the LAH can come in from the front face, or it can come in from the back. And we're going to end up with a racemic mixture of R and S, a 50-50 mixture, which is what a racemic mixture is. And again, this is something that we went over earlier, but it bears repeating because it deals with aldehydes and ketones, which are the topic of this chapter. So let's move on and let's talk about another thing you know. Oh boy, Monsieur Grignard, excuse me, must be PO'd at me. I just put a lowercase g on his name. That's not cool. Recall that Grignard reagents can attack ketones or aldehydes to make a new carbon-carbon bond. Fantastic chemistry. The Grignard chemistry is old chemistry. I mean, this is pre-World War I, but this is still widely used today. I guarantee you that somewhere, somebody in this state is doing a Grignard reaction, widely used to this day. And if we start it with a ketone, and we treat it with a Grignard reagent, we get a tertiary alcohol. And if we start it with an aldehyde, we end up with a secondary alcohol. Here we go. And again, same rationale. Since the electrophilic carbon is sp2 hybridized, the nucleophile can come in, our Grignard reagent can come in, and it can attack from either face of the molecule. So we can end up with a racemic mixture. All right, so nothing really new there. And again, the mechanism for the Grignard reaction is consistent with basic conditions. If you have an acid in there, the acid is just going to protonate your Grignard reagent, and then good night. Okay, goodbye, Grignard reagent. It was nice knowing you. So yeah, everything's under basic conditions. Look what we see. Only negative charges, no strong acids, water, which is a weak acid. So our first step is the nucleophilic attack by the Grignard reagent, and then we can put in water or a small amount of aqueous acid, very dilute, to protonate. Well, let's move on to something new. Everybody knows LAH and sodium borohydride reduction. Everybody knows the Grignard reaction. So let's try something different. And let me introduce you to a new functional group. Yeah, you saw it here first today, the cyanohydrin. So the cyanohydrin is this thing right here. It's a carbon that's got a nitrile attached to it and an alcohol. We call it its own, or we give it its own name. We dub it the cyanohydrin. It says here the cyanide ion is also a carbon-based nucleophile and reversibly adds to ketones or aldehydes to make a cyanohydrin. So if you take your ketone or aldehyde and treat it with hydrocyanic acid, we end up making a cyanohydrin. However, this is an equilibrium, so we have both of them present, and the reaction works a lot better under basic conditions. So we usually use a catalytic amount of base. Well, let's take a look here. If we're under basic conditions, what's going to happen is the cyanide is going to attack the carbonyl, and then we're going to undergo a protonation in the second step. We get a proton transfer. Now, as far as the reaction conditions go, there's a whole bunch of things that are listed here. Now it says, where do you get basic conditions if you have HCN in there? Well, HCN isn't a strong acid. And what we do is we put in potassium cyanide, which is a solid. We put it in with hydrocyanic acid. And that way there's more of CN minus, which is the conjugate base of hydrocyanic acid. So it's a base. And you have more of that than acid. So technically it's basic conditions. Now you notice that if you go back here, first he says just HCN, then here it says KCN and HCN. But I'll tell you something right now, my friends. You go talk to chemists, not only do people not want to work with potassium cyanide, I mean, for obvious reasons, it's a poison, it's very dangerous. To get potassium cyanide, to even use it, the last place I worked, you had to go sign it out. Most chemicals I could just go grab them off the shelf and just use it. But KCN actually has to be signed out because it's so dangerous. And another thing is HCN has a boiling point of 26 degrees Celsius. So it's really miserable to work with. And so anything we can do to avoid working with HCN, we would do. And so the conditions that we're going to use, if I ask you a question on the quiz, I'll try to stick to these conditions. Where are they? I don't even have them, son of a gun. So let me see here. The best conditions, I'm going to write them down here at the bottom. Best conditions are actually not using HCN, but using KCN and HCl. So we use KCN and hydrochloric acid. And that way we don't have to use HCN to make our cyanohydrin. Let me pencil it in here. Let's say we started out with this, carbonyl compound like this aldehyde, and we want to make this cyanohydrin. The best conditions would be to use KCN and HCl because it avoids the use of hydrocyanic acid, which is a big which is toxic and volatile. So there we go. We'll make our cyanohydrin. So this is our cyanohydrin, and you're wondering what the hell would I want to make that for? Pardon my language. Well, there's two reasons. Number one, you can reduce it to make a primary amine like this. So you just reduce it using lithium aluminum hydride and put in some water in the second step to protonate. And the other option is that you can actually hydrolyze the nitrile to a carboxylic acid. So that's also kind of cool, hydrolyze to a carboxylic acid. And you remember that in chapter 20, we're going to do all kinds of carboxylic acid chemistry. So I'm going to put in here chapter 20 because we'll talk about both of these in more detail in chapter 20. But for now, you need to know cyanohydrin formation, and it can be used to make a carboxylic acid or a primary amine. All right. Well, that brings us to our next reaction. Just give me 1 second, which is the Wittig reaction. Yeah, go ahead.
Just out of like pure curiosity,
Yeah.
I just wondered, can you use this as a blocking group?
Which one? A cyanohydrin?
Yes.
I wouldn't say that it would be regarded as a blocking group because there's no way that I know of to go back from the cyanohydrin, back to your ketone or aldehyde. Does that make sense? Like I can't think of a way that you could go backwards.
Oh, I'm sorry. I thought it said it was reversible. That's why I asked.
Yeah. It is reversible if you use these conditions here, and it's reversible if you just use HCN.
Oh, I was just curious. I'm sorry.
Yeah. No, hold on. Let me think about it. It's a good question. I'm not sure. I mean, I can tell you for sure it's never used as a protecting group. Okay, never. Because there's so many other protecting groups that would be more effective. So I can't think of any situation where you would use it as a protecting group, largely because you end up with two really reactive functional groups, an alcohol and a nitrile. They're both susceptible to, the alcohol can be deprotonated by a base, it can be protonated by an acid. So yeah, does that make sense?
Yeah, no, absolutely.
Yeah. I mean, if you were to treat it with acid, you end up with something completely different, and that's not reversible. So yeah, I can't think of a reason why you would use the cyanohydrin as a protecting group. But I understand your rationale. You're saying, well, if it's reversible, and you told me that acetal formation is reversible, why the hell not? Well, there might be, Lindsay, but I can't think of a reason why. And believe you me, there's probably plenty of protecting groups that I've forgotten along the way. All right.